Hello everyone, welcome to my channel Physics Infinity. I'm going to talk on magnetic effects of current once again, where I'm going to talk about the magnetic force, the electrical force between two moving charges, compare the two and then know whether there is going to be attraction or repulsion between them. I'm not going to say that before. After we have done this analysis, we'll come to a conclusion and then we'll talk about that what would happen if the two long parallel wires which carry current, will they have attraction, will they attract or will they repel? First of all, let me see the situation where two particles having mass, each having mass m, but they are having charges q1 and q2, both positive say, and they are moving with velocity v arrow parallel to each other along y-axis, that is along j cap. So here we are, q1 arrow and q2 arrow are moving with velocity v arrow, that is the direction of the velocity. So in terms of vectors, well, v arrow is along j cap. So this current element and this current element, both vectors have direction j cap. Now what happens? This magnetic agent, that is, or element which is a magnetic agent, q times qv arrow is a magnetic agent. This creates magnetic field at the site of the other agent, that is q2v arrow, and the other agent experiences a magnetic force. The magnetic force F21 arrow magnetic is F21 arrow is the force on Q2V arrow due to the field of Q1V arrow. So it is Q2V arrow cross B1, where B1 arrow is the field at the site of Q2V arrow due to Q1V arrow. Well, Q2V j cap cross the magnetic field due to Q1V arrow at the site of Q2V arrow, constant, magnetic field constant, mu naught upon 4 pi Q1V agent divided by d square into minus k cap. Sure, I have made use of the Biot-Savart's law to get into this. The fact that I am using mu naught, understood, I am taking the case in free space or air, because in air the mu naught and epsilon naught are nearly taken same as that of free space. If I work that out, then I find that the magnetic force on Q2V arrow comes out to be mu naught by 4 pi Q1 Q2 V square divided by d square, and then I have j cap cross minus k cap, that gives me minus I cap. So this means this agent gets attracted towards the other magnetic agent, and the same is vice versa. So mutually they get attracted. So there is magnetic attraction. Keep it. Now don't forget that there is also Q1 which is creating electric field at the site of Q2, which is d away from there. Let's work out the electrical force on Q2 due to Q1. K 1 by 4 pi epsilon naught Coulombic repulsion. This is going to be Coulombic repulsion. Q1 Q2 upon d square I cap. This was minus I cap. This is I cap. So this is repulsive. Fine. I take the ratio of the electrical interaction with the magnetic interaction. Electric is repulsion, magnetic is attraction. So F21 electric upon F21 magnetic, taking the magnitudes of course. I just put the figures. Q1 Q2 upon 4 pi epsilon naught d square upon mu naught Q1 Q2 V square upon 4 pi d square. Q1 Q2 upon 4 pi d square cancel, and I get the answer 1 upon mu naught epsilon naught V square. Now according to electromagnetic theory of light, 1 upon mu naught epsilon naught is c square, where c is the speed of light, 3.0 10 to the power 8 meters per second. So I find the electrical force upon magnetic force as c square upon v square. Now, according to the Einstein's postulate, no material particle can achieve the speed of light. So certainly c has to be greater than v. So c square upon v square still. So electrical force will definitely dominate magnetic force. In any case, out of the three classical interactions, gravitational, electric and magnetic, strongest is electrical, then magnetic, and the weakest is gravitational. So electrical interaction dominates the magnetic interaction. Electrical is repulsive, magnetic is attractive. So overall, the parallel moving charges will get repelled. Now, there is a question that arises in the mind of students. That is, if I take two parallel long wires, and if the current in this is, let's say, I1, and in this is, say, I2, and the two wires are separated by D, then the force per unit length is on each wire is mu naught I1 I2 upon 2 pi D, and that is attractive. So the two long parallel wires get attracted to each other due to magnetic interaction. Now, why not repulsion? Because after all, the current flowing, if the current is going like this, that means electrons are going down. So I can take the jolly well situation that in these two scenarios, electrons are moving parallel to each other downward, because if the currents are going up, means electrons in the wires, conducting wires, are moving down. Magnetic, as far as magnetic is concerned, there is attraction, and we have just learned electrically there should be repulsion. So why don't the two wires get repelled? No, they will not get repelled in that case, because over there, though there is magnetic attraction, but there is no electrical interaction. Why? Because both the wires at all instants, while the current is flowing through them, are electrically neutral. So no question of electrical interaction there. That is why two parallel current carrying wires placed near each other eventually get attracted due to magnetic attraction only. So with this, you have learned magnetic attraction, electrical repulsion, and you also now have learned that why two parallel current carrying wires attract each other only due to magnetic interaction, and why electrical interaction is not there. I hope you have enjoyed the video. If it is so, please subscribe my channel and like my videos, give some thumbs up.